Okay, so thank you for coming. I'm Joseph Bradley, and I'd like to talk to you today about practical machine learning pipelines using Spark's machine learning library, or MLlib. So just as far as my background, I have a background in machine learning, and I'm an Apache Spark committer working as a maintainer on MLlib, and I'm a software engineer at Databricks. So just a little bit about Spark, 1 minute overview. Distributed computing engine, which is basically built for speed, being easy to use, and doing sophisticated analytics. And of course, it's an Apache open source project. So in addition to the sort of core distributed computing engine, there are multiple higher level libraries built on top: SQL or databases, streaming, machine learning, and graph processing. And having this ecosystem is, I'd say, like one of the best things about using Spark. It has very concise APIs in multiple languages: Python, Java, Scala, and actually R is coming in the next Spark release very soon. There are over 500 enterprises we know of using or planning to use Spark in production. And perhaps another strong vote of confidence is the growth in Spark contributors. And this is a plot of contributions from GitHub in the last 5 years, just contributions per month. And you can see it started as a project with a handful of people at Berkeley and has grown to over 100 individual contributors per month. So in addition, as it's been growing, of course, the user base has been broadening. And we've moved sort of from the very early adopters through data engineers. People used to say Hadoop, MapReduce, functional APIs, sort of like hardcore programming. And I think as its user base has broadened, we've moved to see even more people from, say, data science or statistics backgrounds. People used to tools like R, scikit-learn, Python Pandas, and so on. And so as the user base has grown, we've made efforts to try to make it easier and more accessible to people from these other backgrounds. So that's what I'll really be talking about today, using Spark for data science. And that'll come in 2 parts. The first is I'll mention data frames, which basically allow for intuitive manipulation of structured data, and in Spark's case, distributed structured data. And these are going to be used as sort of the de facto machine learning data sets, which will feed into ML pipelines. Now, pipelines are a concept which we've developed which allow for basically simple construction and tuning of ML workflows. But first, I'll talk about data frames. And just in case you haven't worked with them yet, if you look at Google Trends, you can see why a lot of people have started using them. This is in the last several years. In the last couple of years in particular, usage has skyrocketed. And this is why. First, it's a simple data representation. Here's a simple data frame. There are 3 columns: department, age, and name. And you can see they may have different types. Department may be a string, age an integer, and so on. So data are grouped into named columns, a very familiar type, both to people coming from data engineering and from statistics. The other big part of the data frame idea is the API. So if you've used Spark before, you're likely familiar with the RDD, or basically the distributed data set in Spark's lingo. Now, it provides a very simple API where you can do map operations, just say passing a Lambda function in, reduce by key, other maps, collect data back to the driver to get your results, and so on. But as you can see, like this query on this very simple table may be hard to parse. And actually, there's a bug in it. And it may be hard to spot because you're doing things like working with tuples, without names, using indexing. Instead, we can write this in the newer data frame API. And you immediately know what it's doing. We take our data, we're grouping the rows by the department column, and then within each department, we're computing the average age. And so you can immediately see how powerful this is, this sort of domain-specific language for common tasks. This includes things like projection, filtering, aggregation, joining. And at least in Spark's case, support for metadata for columns, and also user-defined functions, or UDFs. So Spark data frames use an API inspired by R and Python Pandas data frames. So if you're coming from those, they should be immediately familiar. However, we have support in Python, Scala, Java, and actually R in development. There's also Pandas Integration, where you can immediately convert in a single call to and from a Pandas data frame. Now, the difference between this and R and Python Pandas, I'd say, is that it's distributed. Same kind of simple API, powerful operations, but working efficiently on a computing cluster. And finally, it's quite highly optimized. So just to give you an idea of what I mean by this, I'll compare with Spark's Rdds. So this is a small example just run locally on a small data set, just 10 million integer pairs. But even on this small problem, it gives you an idea of what I mean. It's showing aggregation of 10 million integer pairs in terms of seconds, so to the left is better, and comparing data frames versus Spark Rdds in Python and Scala. And so you can see two things immediately. First, for Rdds, there was a difference in time between the Python and Scala. But with data frames, there's no longer that disparity. And it's because of unified implementation. Also, even for this very simple query, data frames are faster than Rdds. And if you're familiar with Spark, you may think this is odd because data frames are actually backed by Rdds. The difference is that data frames take advantage of the Spark SQL Catalyst optimizer, which does some query optimization, and even on a really trivial thing like this, makes significant speedups. So what I'd like to do is just to give you a quick idea of what this looks like in practice. So I'm going to switch out of this and hope that the Wi-Fi holds up strong. And I'll be doing this demo in the Databricks cloud platform, which is basically the Databricks product for running Spark, backed by Amazon EC2. But you can run these same commands at home, other than some of the visualizations. It's just nice for not having to worry about spinning up clusters and all the management behind. So what I'm going to do is load the 20 news groups data set as a data frame from Parquet. This is a very common machine learning data set, just 20 sets of news group articles from different topics. And Parquet is just a nice columnar storage format. So I'll load this, and I will give the caveat that this is running on a single node, but it's mainly meant to show an example of the API and the ease of use. So we have 11,000 articles, and we can, for example, look at them and see we have an article ID, a topic, and some text. So what we're going to do with this is just some queries to show off the data frame API. So here I have the documents. I'm going to group by the topic and then count them. So basically what we'll get is, within each topic, a count of the number of documents we have. And we can see medicine, electronics, and so on, and basically get an idea that we have a pretty even distribution of topics in this data set. We can do other queries with data frames. We can filter, say, looking for topics which are science.medicine, and then select just these medicine articles and look at them. Here it's one talking about Gaucher's disease distribution. So what I'm going to do, just to show off one more query, but also to prepare data for later on in the demo, is create a new column. So I'm using this with column method, and it's creating a label column basically by taking the topic column and looking to see whether it's one of the science subcategories. So our goal is going to be later on to distinguish science articles from non-science articles based on the text. And we've basically used the data frame API to do some simple pre-processing so that we can prepare it for the ML pipeline. And you can see we have some 2,300 science articles, and the rest are not. Cool. So I'll switch back. And to sum up, so we've looked at data frames, working with structured data, using a familiar API to those coming from R and Python, but backed by a distributed optimized implementation. And we're going to use these as our data sets for ML pipelines. And I'll demonstrate construction and also tuning of the parameters in a ML workflow. So just 30-second background, Spark MLlib is one of the 4 sort of higher-level libraries which ships with Spark. It started at Berkeley, shipped with Spark 0.8, and a few releases later has contributions from some 50-plus organizations, over 100 individuals, and a pretty wide coverage of distributed algorithms. And I won't have time to go through them, but you get the idea. Have classic ones: classification, regression, clustering, recommendation, feature extraction, and also some lower level or less common ones, such as statistics, linear algebra operations, frequent item sets, model import and export, and now pipelines. So to motivate the need for pipelines, I'll mention that ML workflows, of course, are complex. Here's a simple, super high-level view of one. You load your data, you extract some features, you train that ML model, and you evaluate it. Of course, in reality, each of these elements might be pretty complex. You might have multiple data sources. To extract features, you might go through some whole series of feature transformations, which might depend on the type of data source. When you train a model, that might actually mean training multiple models and then, say, averaging the results in some smart way via an ensemble, and then finally evaluating. So yeah, basically, in this demo, I'm going to show a very simple pipeline, but you get the idea of how it can quickly become complex. And looking at that complex pipeline, you can see some of the difficulties are, say, specifying it in the first place, after you have it, inspecting it and debugging it if something goes wrong, rerunning it in exactly the same way on new data, and also tuning parameters. Each of these pipeline components might have multiple parameters, and tuning them based on your data set might improve speed, accuracy, and so on. So we're going to look at these and discuss ML pipelines. We'll look at these and discuss ML pipelines using a simple example of text classification. So our goal is going to be looking at that 20 news groups data set, given a text document, predict its topic. Our features are going to be the text. We're going to use those to predict a label, which will just be 0, 1, not about science or about science. So here's what our workflow will look like. And I'm going to describe basically how we'll go through it. And you can imagine how it could be generalized to other applications. The point is not this particular application, but how you specify the workflow. So for loading data, basically we rely on the data sources for data frames. There are a number of built-in ones, but there's also an external data source API on which we and other people have built other data sources support. Avro, CSV, and so on. So given that we load the data using the data frame API, we basically start this pipeline with a data frame. And I'm going to describe how we go through this pipeline basically by representing the current data schema. After we load our data, I'll say we have text, a string, and a label, an integer column. So we have 2 columns in our data set. And as we go through the pipeline, the same data frame is basically going to flow through and be augmented with new columns. So the next step is feature extraction. And actually for this ML problem, I'll make it a little more complex and have 2 levels of feature extraction. First, we'll tokenize the data. And what that means really is taking the text of an article and outputting a new column of words. So the new column will be labeled words and have type sequence of string, just like all the words in the data. Then we'll go through what's called a hash term frequency module, which will take that words column and output a new column of features, which will be basically a numerical vector, in a format which is very friendly for ML algorithms. So I'm highlighting these in blue because these are basically transformers, and this is an abstraction in the pipelines, which takes one data frame and produces another data frame. And you'll note that each of these components can basically select from any of the previous columns and output one or actually multiple columns of its own. So for training a model, we're going to be using logistic regression, arguably the most common or useful model in practice. And it will pull from the label column, which we haven't looked at yet, as well as the features column. It'll train a logistic regression model, and then that model can output a new column, which is the predictions, again, an integer, which is just that model's estimate of the label for each of the rows in our data set. So this is red, indicating that it's an estimator abstraction, which takes a data frame and outputs a model. If you're familiar with, say, scikit-learn, we tried to stick with familiar APIs. So they have concepts like transformers and such, basically to make it familiar, but of course backed by distributed data frames. And then finally at the end, we'll evaluate, and that will look at the true label column and our predicted label column, compare them, and basically tell us how we did in some metric. So you'll notice by default, we're always appending new columns. Now the pro of this is that at the end, you have a single data frame, and you can go back and inspect intermediate results in any of the columns generated during the pipeline. The catch is, of course, you don't want to keep all that data around, but this is made efficient by data frames, where if, say, you never want to look at a particular column, you don't necessarily have to even instantiate or materialize that column, but if you need to, then you can. So I haven't actually mentioned what a pipeline is, and that's basically a concept which wraps this critical part of our workflow. And the point of storing this in a single class is going to be, well, there will be a few. First, after we train a pipeline, we may get new data and want to run the same pipeline in exactly the same way. And this will let us do it easily from a programming viewpoint. The other critical point is parameter tuning. So in this pipeline, there may be a lot of parameters, but I'm just going to look at a few. Say logistic regression. It has a regularization parameter, and basically tuning that can help adjust for having too little data, a lot of data, different types of data, and basically affect the performance of your final model a lot. So we may want to sweep over a few values and see which is best based on our evaluator. Hash term frequency actually has another parameter, which is the number of features. It outputs this feature vector, and we don't know a priori, is it sufficient to represent a text document, using 100 numbers in a vector or 10,000? So what this will let us do, the pipeline concept, is basically wrap this object and optimize however many parameters inside we want jointly. And we'll do that using the cross-validator class, which takes an estimator, in this case the pipeline, a parameter grid, and an evaluator, which basically says, for each model, train for every point in our parameter grid, how well it does. And then it'll find the best parameters. So this is something you can do on your own, but basically it's a lot of rote programming where it's easy to make mistakes and which you really don't need to do, you really shouldn't need to do on your own. So I'll demo how that works. Cool, so we just created our labels, science or not science. And now what we're going to do is this. We'll classify the newsgroup articles with 3 stages of a pipeline: tokenizing, translating from articles to bags of words, hashing TF, which will turn those words into feature vectors, and logistic regression, the actual model. So the way we'll specify this is like this. We take a tokenizer, and we set its input column and output column, basically pointing to that part of the data frame that we need. Hashing TF likewise takes input and output column parameters, and we can also say set the number of features. Logistic regression may take other parameters, and so on. And then finally, to specify the pipeline, we can simply set the stages in an array in the order in which they're called. So to fit this, we just call pipeline.fit, passing in the training data set. And what it's doing is going through each of these stages in the pipeline, tokenizing the data, generating feature vectors, and so on. Cool, so now we fit the pipeline, and we can look at the results. To do that, we're taking that fitted model and transforming the data set, and then we can select the elements we're interested in. Say, the topic, we predicted 0, and indeed it is not about science, so we were correct. We can also get, of course, more useful measurements of how well we did, such as, say, area under the ROC curve. So what I did here is define a function computing just that on our training data, and you can see we get 0.999, which is almost perfect, almost 1. But of course, the model is going to be overfitted. And the way to see that is to compute this ROC metric on the test data, where we get 0.899, significantly worse. And so, of course, we can do better than that. And the point is that we can now use this pipeline to do cross-validation, tuning these hyperparameters by searching over a grid of the number of features and the regularization. And we'll optimize based on this evaluation metric. So to specify the parameters, you basically say, over a number of features, we want to test these values, regularization, these, and it builds a grid of all of the values to test, and then we can test them. So what this is doing is cross-validator takes our pipeline, which it needs to choose parameters for, an evaluator, which basically tells us, for each of the elements in our parameter grid, how well are we doing? And finally, the parameter grid, the set of parameters to sweep over. And here, I'm just doing 2 folds of cross-validation. Of course, in practice, you might want to do more. But this is just a test. So after this is done, it's going to have computed for each of these points in our parameter grid the average error over a couple folds or random splits of the data. And of course, this is something which is pretty simple to do. If you're only tuning 2 parameters, you can do it by hand. But if you're doing a complex pipeline, what this allows you to do is tune all of these parameters sort of jointly. So we can look at the best, oops. Let's see. Parameters. And here, let's see if I remember the syntax. Okay. Okay, this is embarrassing, but basically, if I remembered the correct call, you could extract the parameters, the optimal parameters. But what we can see is that we actually have improved, because when we run this best model on our test data again, we've improved from 0.89 to 0.93. So finally, we can save the predictions. And here, basically, I'm saving to some location on HDFS where I'm saving the article ID and the predicted label. So it gives you a sense of what pipelines are able to do. So to recap, ML pipelines have this tight integration with data frames, use a familiar API based on scikit-learn, and permit simple parameter tuning. There are some things I didn't really have time to get into. They provide schema validation, which is basically, rather than running your pipeline for a day or whatever, and then finally at the end, you made a mistake and it fails, schema validation basically checks the metadata as it flows through your pipeline before actually physically running it with the full data set. We have user-defined pipeline component support, where basically we have these transformers, estimators, evaluators, and users are able to plug their own models into these APIs. And finally, we have support for composable and directed acyclic graph pipelines. In the demo I showed, it was a simple linear chain, but really it can be You can have pipelines within pipelines, as well as pipelines which are basically general graphs as long as they're direct and acyclic. So there are a number of things which are coming up. In Spark 1.4, which will be released soon, Spark R is going to be supported. And this was a project at the Berkeley AMP Lab, but now has been merged into Spark itself and should be very useful for a lot of data scientists. Pipelines themselves will be graduating from an alpha component, so we hope to gain a lot more testers and users. So there'll also be many more feature transformers. At the beginning, I showed a list, and you probably couldn't read it, but basically, there's been a lot of effort to include many common feature transformations, such as one-hot encoding, assembling multiple vectors into a single vector, indexing for different types of categorical data, and so on. There's also a much more complete Python API. So in the future, some of the things which we'd like to add are an API for R data frames and pipelines, more ML algorithms and pluggability. So pipelines are essentially a higher level view of the traditional MLlib algorithms. There are, however, some algorithms, such as clustering, which are not yet in the pipelines API, but those should be added soon. We also are working with some other partners to add improved model inspection, where if you, for example, you've used R has a great summary of models. If you show or display the models, you can get both sort of like a text summary of how well they did, and also some great visuals, which basically give you a good sense of whether you're training the right model or not. So you can learn a lot more next week at the Spark Summit, which I'll put a plug in for. Check it out. Hope you're coming. And I will also mention, coming from Databricks, which was founded by the creators of Spark and still largely driving its development. But I'll also say what I was demoing in is Databricks Cloud, which is, I'd say, the best place I've found to run Spark, handling a lot of both lower level and higher level stuff, REST APIs, and so on. And of course, guess what? We're hiring. Please inquire. I will leave a few links, which I hope you'll find useful. The Spark documentation, of course, has a lot of info, including a detailed user guide on pipelines. There's some blog posts on pipelines and data frames, which have a lot of info too. The Databricks platform, and also, very exciting, there are several MOOCs being basically co-sponsored with Berkeley on edX, an intro to Spark, and also machine learning using Spark. And I'll finally mention Spark packages, which has an increasing number of machine learning algorithms, which are different from the ones which are in MLlib itself. So you can definitely check that out, either as a user or as a developer if you're looking for users. Cool. And so with that, I'd like to thank you for listening and ask if people have questions. Thanks. Oh.
So you were showing that classification for the text mining, right?
Right.
So if there are more than 2 target variables, still the same thing, it will work?
Right. Yes. So that was just binary classification. There is support for multi-class from certain algorithms. So we have multi-class support for logistic regression. And I'm talking about in 1.4, which will be out very soon. Logistic regression, decision trees, and random forests.
And if you don't have that training data, because it's text mining, right, to begin with, then have you tried that?
You mean, what if those labels are not available?
Yes.
Right. So I'd say then you're in less of a, supervised setting and more, say, unsupervised, where you might use something like clustering. And there is support for things like...
or LDA?
Yeah, LDA, where we have both online LDA and EM optimization. There's also other types of clustering like k-means, Gaussian mixtures, and so on.
Hey, so in your example in the pipeline, where you're showing the grid search over, the hyperparameters, does it intelligently figure out, let's say you have 2 here and you have 3 here, right? Does it figure out that, I've already computed this one once, so I don't have to recompute this every time?
So I think there are multiple levels to that. In terms of you have a, say, 3 by 3 grid, you do only train at most 9 models, or run the pipeline 9 times. There are additional savings which we've implemented the API for, but have not implemented for specific algorithms. Those kinds of savings, are things like, say you're tuning the regularization parameter, then especially if, say, you're doing, say, linear regression, it can be very useful to, say, train with the largest regularization and then use that to warm start for later things. We have not done that yet, but we've thought about it and have basically provided the API for it.
Okay, sure.
But yeah, we want to.
Okay, cool, thanks.
Yeah.
Hey, so in this setting, you use batch model to train the model, but can we later use the trained model in Spark streaming, for example?
Right. Yes. So, Spark streaming essentially operates in mini batch mode. And so what you'll need to do to use those models will basically be to serialize it and save and then load it back in whatever streaming job you have later. So with that, MLlib itself has the traditional API has support for model import and export. So you can use that. And then within the streaming job, basically, you'll need to make sure that the data are in whatever format that model is expecting. Right, you can use it like other Spark objects, right?
Okay,
Or,
all right,
yeah.
thank you very much.
Sure.
The second question was, in addition to grid search, do you support random search or Bayesian optimization?
We don't. We've talked with some of the people, for example, from Berkeley ML-Base project, where they are doing some, research into fancier methods. I think that will be a great thing to add in the future.
Right.
Don't have that yet.
All right,
Yeah.
thank you.
Sure.
Hi. What are the appropriate use cases for this model? Like just read only, or can I use for writes purposes also?
So to make sure I understand, you're talking about after you've trained a model, then can you edit it, or?
No, for the read data or something. What are the appropriate use cases for the?
Right. In general, this pipelines framework fits sort of 2 modes, where the sort of 2 calls you can make are fit and transform, where fit takes some estimator, say logistic regression or a pipeline, and produces a model, which can then be used to transform your data. Where transform, in the ML case, really means make predictions or transform features into some other format. I'm not sure if I'm answering.
Oh, yeah, okay.
But,
and for the Spark car, you said you're looking for committers. Suppose if I'm interested, where should I go and register for that? The Spark car.
Oh, yeah, so Spark R is, it was a research project. Now it has been merged into Spark Master and will be in the next release. So you'll be able to use it immediately. Well, either right now, if you compile it yourself, or in the release, which will be available soon. If you want to actually contribute to it, then basically I'd recommend checking out, we always operate basically through Jira, GitHub, and the user list, or in dev list.
Okay, thank you.
And in particular, pinging the dev list would let you get feedback about what needs work, where to start.
Thank you.
Sure.
I have another question.
Oh,
so what is the story with packaging in R? So usually there are a hodgepodge of different packages that you have to install. How do you deal with that in the distributed setting?
Right, so I'll admit
And same with Python, by the way. Do you use Java Python, or is that real Python?
Oh,
Like CPy.
oh, I see. So, I mean, the Python code in Spark itself and like what I use when I'm acting as a user of Spark is just traditional Python. As far as like packages, basically if you are using them, there are two ways to use them, either on the worker or on the driver or the master node. And basically they need to be installed on whichever
Okay, so
you're
say
using.
if I use like NumPy or
Right.
scikit-learn or something like that,
Right.
I have to pre-install them on all the machines and
That's right, yeah. And MLlib itself basically assumes availability of NumPy. It does not assume SciPy, although it can take advantage of it if it's there.
okay,
Right.
so MLlib, now I'm confused. So MLlib, is that a Spark library or is that a
right.
Scala library or Scala or Python?
So
or is it-
MLlib is just another part of Spark. And like the rest of Spark, most of the internals are written in Scala, but APIs are provided for Python, Java.
So say if I train my model using Scala, and then I have another code that actually uses this model in Python,
Right.
is that possible to do?
So that is possible if it's easiest if you go through the import-export which MLlib provides, where there you can save and load in any of those languages, and it handles it seamlessly. If you wanted to actually do the conversion yourself, it's a bit more intricate. Right.
Okay. All right. Thank you.
Sure. Can you come to the? Oh, okay. Oh.
Could you elaborate a little bit on the ML export? Is that something you could
Right.
actually export out of
Right.
the system into something like Storm, or is it something only within the ecosystem?
So in 1.3, we had import-export for basically a Spark-specific format. And that was, basically we looked around and there was not a clear format to use for distributed models, where some of the models like matrix factorization may not be storable on a single machine. That export has expanded for this next release, but also there's been PMML support added for a number of models. So that should, help with, I think, a lot of use cases.
Just a quick question. Do you have any support for survival analysis, like Cox proportional hazard?
Right. There is not right now. I think that some of those things may become easier to work with as, say, indexing in Rdds and windowing become available. So they'll become easier to implement. But yeah, there's not like a
You think it'll be
method
on
for
the
that.
roadmap at some point, or is that what you're saying?
There have been a number of questions about it, but I should not make promises about like ETA.
Support as far as being a producer or consumer?
Right. PMML support is just producing it. Consuming PMML would be great. There isn't a license, like a library available, which we could just pick with a friendly license for importing PMML, but there was for exporting. It would be great to add in the future, though. Yeah. Okay. Great. Well, thank you, and I think it's about time for a next one.